This is lecture 19 of Surveying 1, and I have titled it Measurements, Errors, and Mistakes. In a way, you could say it's a prelude to a series of lectures on errors analysis, and more specifically, random error analysis. We won't get into it in a lot of depth, but we certainly will have a lecture or two, enough so that you can do some mathematical computations either in your homework assignments or from your lab work. So this is a really important part of surveying, and I want to kind of get into this by first talking about something we've already discussed, and that is that accuracy and precision in surveying do not mean the same thing. Now, in ordinary English speech, we sometimes use those words synonymously, but in surveying, they're definitely different. So the way to summarize it is that the accuracy reflects the result and precision reflects the methods. So another way to look at accuracy is that accuracy is how close a measurement is to the true value, whereas precision is the nearness or closeness of measurements to each other, not necessarily the true value. And precision may also indicate the quality of the instrument, or the quality of the methods, or even the quality of the people. And very often, it's kind of a combination of all three. So it's very often a qualitative statement. I also want to talk about what an error is. An error, all by itself, is simply the difference between a measurement and the true value. So if I was writing an equation, I would say the error is equal to what you measure minus the true value. So remember, in this case, that if you have a positive error, it means that your measurement was larger than whatever the true value is, and if you have a negative error, that the measurement is smaller than the true value. And this is something I expect you to remember. And then again, this is review, but a mistake is the same as a blunder. It's preventable through careful attention to all your processes, and it usually requires repeating your measurements. The nice thing about blunders when they are large is that they're easy to detect, but when they are small, they often get analyzed and managed with errors because you can't distinguish between them. So when blunders get small, they kind of disappear. And I don't mean they literally disappear, they simply get grouped in with errors and are actually miscalled or misnamed, but we have no way of telling the difference between the two. Now, errors analysis is a really important part of surveying, and that's why I've chosen to kind of put it here at the tail end of our discussion of surveying, because I think it's a little too much for surveyors, for surveying students to kind of grasp all these till they've had better coverage of the actual material on how to perform surveys, and I've actually had a little bit of field experience. What I like to say is that anybody can measure, but only surveyors analyze. Now that's not literally true, because there are many scientists, many mathematicians, many statisticians who also analyze. But when it comes to measuring the earth, there are many people who claim to measure. A lot of people who claim to measure because they can go out and buy the same instruments that surveyors do and say, I made that measurement. But most of the time, they're incapable of doing any of the analysis or even the simple, even understanding the simple concepts that we've talked about so far up through this slide. So if we have people who call themselves surveyors or who say I'm doing surveying, but they don't show any evidence of doing analysis, then they are not surveyors. And by the way, that's kind of the standard I will apply more and more as you go through this experience in education in surveying. Now, one of the questions I like to ask professional surveyors, because many of them actually flunk this question, is what do clients want? Do they want accuracy or do they want precision? Well, if you really understand what this is, and you may have to take a while to think about this, it may take days or even weeks for you to fully understand this, but for now you may want to just memorize it. Clients only care about accuracy. They want to know where to dig. They want to know where to build that wall. They want to know if their neighbor just cut down their tree or not. And so that's accuracy. Clients don't care about precision. However, it turns out that if we want to make accurate measurements, we generally have to be very consistent at what we do, and that means that we have to bring precision into the picture as well. We'll talk about that more in a future lecture. I want to review again the sources of errors. Not blunders, not mistakes, but errors. So they come from nature, and we call them natural errors. They come from instruments, and we call them instrumental errors. And they come from people, and we call them personal errors. The mistakes that, errors that people make. Now keep in mind that there's no such thing as a natural blunder. Nature doesn't actually create blunders. Instruments sometimes, however, can have blunders because maybe, especially with electronic instruments, they haven't been programmed properly, and so there's a mistake that some human being made in the original programming that causes an erroneous calculation that results in a false answer to an implied question or a direct question that the surveyor or the operator of the surveying instrument has asked. So it's possible to have blunders from instrumentation today. It wasn't very common before electronics, although there are a couple of ways that could happen too. Most of the time, people commit blunders, but that's not to say people can't commit other types of differences from the correct value that are actually errors and not blunders. So you have to be very careful. Just because there's a discrepancy caused by a human being doesn't necessarily mean that it's a blunder. It could also be an error. And probably some of the easiest ways to talk about this is when you're taping and you're holding a plumb bob over a point, assuming you're exercising the correct amount of care and holding the tape up off the ground, and you have a plumb bob projecting the end of the tape down to the point on the ground, there's always some uncertainty in how well you can line those two places up. That is, the tip of the plumb bob and the point on the ground, and making sure that when you do that, the plumb bob is truly vertical. And those would be called personal errors. Whereas if you held the plumb bob string on the wrong graduation on your tape when you're doing all this, that would be a blunder. So humans commit blunders, and humans commit errors as well. And then you need to be aware, in addition to the three sources when it comes to error, that we have two types of error. One is called systematic, and the other is called random. And so systematic is easy to understand. We've talked about this already in quite a few different ways. Best example would be a steel tape, and it was calibrated, found to be exactly 100 feet long at a certain temperature, and now you're using it when the temperature is 30 degrees less. Well, the tape has contracted, so it's not as long. It's not 100 feet long anymore. So every time you lay out 100 feet with this tape, it's short by a certain distance. And if you laid out 400 feet, it would be short by 4 times that shortening effect for 100 feet. So it's very systematic. So most of the time, systematic errors are exactly proportional to the distance measured. Not quite exactly, because if you paid attention to the section on electronic distance measurement, there's an example of a systematic error that could occur that I haven't really talked about much, and that is having the wrong prism constant. Technically, that would be a blunder, but it's possible that you can have a distance that's measured that's off by, say, 5/100ths of a foot, whether that distance happens to be 50 feet, 500 feet, or 5,000 feet. So in that case, the systematic error applies per measurement. And then we have random errors, and random errors is actually where we are going to spend a lot of time, so I'll come back to it here soon. When it comes to systematic errors, and this is how you get to accuracy, by the way, when you make measurements, you need to know everything there is to be known about the system. And what do I mean by the system? So that's all your instrumentation. So if you're using a steel tape, that's not just the steel tape, it's the plumb bobs, the tension handles, the thermometers, and all that stuff. If you're using an EDM, it's the prism, the tribrax, or the prism poles that are being used to hold it, as well as the total station of the EDM, and so on and so forth. So you need to know everything about the system, because then you have the environment. What's the temperature? What's the atmospheric pressure? What's the relative humidity? What's going on with the wind? What's going on with the sun, and so forth, that can all induce different kinds of systematic errors. And finally, the people themselves can induce personal errors that are systematic. So what I say here is, if you know everything about the system, then systematic errors can be completely eliminated, so that all you are left with is random errors, and therefore much higher level of accuracy. And this, by the way, is exactly how you get to accuracy. And so when you are doing a survey, you need to know how accurate your measurements need to be, so that you know which of the systematic errors to ignore and which ones you really should consider and apply. Which means you need to run through the math and do what we call a pre-analysis to determine what the level of systematic errors are going to be. So the big question when it comes to this, as I said here, systematic errors can be eliminated. I could have said can be totally eliminated. Not exactly totally. Why? Because the big question is whether we know everything about the system. For example, when we do GPS observations, there's a lot of things about the troposphere, that's the part of the atmosphere we live in, as well as the ionosphere, which is quite a bit above our heads, that has lots of ionized particles in it. These both affect GPS radio waves. And it's still being worked on. People are still working on understanding what that is. So we can't necessarily eliminate all systematic errors due to atmospheric effects when we use GPS if we desire a certain level of accuracy. All right, so let's talk about random errors. So random errors occur with each measurement. Every time you make a measurement, there's always some uncertainty in the measurement that's totally random. It's due to our inability to be perfect, both in terms of our instrumentation, in terms of ourselves, for example, the swinging plumb bob, or the inability to perfectly center an optical plummet on a nail, or the inability to perfectly center a crosshair on a target when we're measuring angles, or the inability to exactly read the level rod reading with the horizontal crosshair, and so forth. There's always a little bit of variation because you might be doing a little bit of interpolation, reading between the graduations and so forth. So random errors always vary in sign. Sometimes they can be positive, sometimes they can be negative. They also vary in magnitude. Just because you have a random error of such and such now, it doesn't mean you'll get the same random error the next time you repeat that same procedure. It might be larger, it might be smaller. But one of the true things about random errors is that they're seldom very large. So if you have a large error, or what appears to be a large error, you need to look at it very carefully, because it may turn out to be a mistake or a blunder instead. And so one of the truths when it comes to random errors that you should be aware of is that if the same thing is measured over and over again, so we have a distance that we measure over and over again, an angle that's measured over and over again, a GPS position that we determine over and over again, the more times we determine these positions, these distances, these angles, and average them, there'll always be some variations due to random error, and the more we have in the mix, the better the chance that the random errors are being averaged out. And this is where the other part of redundancy in surveying comes in. So I often talk about surveyors doing their work without practicing redundancy. One of the reasons they need to practice redundancy is to remove the possibility of blunders or mistakes by measuring the same quantity a different way or from a different place or something like that. But the other part of redundancy is that the more times you measure something, that the average will always have a greater reliability than any single measurement. And that's partly because your random errors are averaging out if you have enough of them. Now, is it enough to have just 2 or 3? No. That's what you've pretty much been doing in your classes. You need to have 10 or 15 or 20 or 30 before you finally start to average them out. So even a half dozen can be very helpful. And so this is something in terms of how accurate a result you're looking for that you need to start thinking about. What is my threshold? Well, measuring it twice, measuring it 4 times is rarely enough to average out the random error completely. So here's a case that I just want to talk about. This is a case I often run into. Surveyors tell me something like this all the time. A surveyor says he completed a project and the precision of his survey came out to be 1 in 50,000. Well, most surveyors would be pretty proud of that. They'd say, hey, I do pretty good work. The question is this really good? And so you start by asking, will the survey get the same result, the same precision of 1 in 50,000 if it gets repeated? Because it's possible to accidentally do well. The other thing you need to ask is, were the systematic errors and the blunders in the survey eliminated? In other words, was enough analysis done to make sure there were no blunders? Because you can have blunders and still have a high precision, because they could cancel out too. Or do you know if the surveyor paid attention to the system and removed systematic errors? So let me give you a couple of examples relating to blunders and systematic errors. Let me start with blunders. So one of the things you could do, for example, is measure a perfect square with a 100-foot tape. And you could say, I closed within whatever a fraction of a foot would be that give you 1 in 50,000 for your closure. But what if this tape was actually has a blunder in it, the manufacturing process? And this actually happened to me. So here's a steel tape, and there's markers every foot. Well, I had a particular steel tape that was missing one of these markers. And so the tape was actually 99 feet long. So we had a traverse or a set of measurements around a square that closed almost perfectly. So we got 1 in 50,000, but every one of the distances measured was actually an entire foot short. So you see how we can have gross inaccuracies even though we have high precision due to blunders. Now let me talk about systematic errors, and we can use the same figure. I'm going to remove all this here. And let's say now that the sides of this rectangle are each 10,000 feet long. So if they're each 10,000 feet long and the surveyor went out and measured this with an EDM and didn't pay any attention to the parts per million correction that needs to be applied due to temperature and pressure. And let's say it was a very cold day, a very hot day, a very high pressure day, a very low pressure day. Let's say, just for talking purposes, that the surveyor should have applied a ppm value of plus 40. But the surveyor was so inexperienced, didn't even look at the ppm value because he'd always been told, well, they're parts per million, how bad can that be? Surveyor didn't even notice that the actual display of the parts per million setting when he used the EDM to measure this 10,000 foot survey was minus 10. So this means that he had a total error of 50 parts per million. Now, without even applying the correction of 50 parts per million to the 10,000 feet, let me show you how you would do this analysis. You actually know how to do this. 50 parts per million is 50 over 10 to the 6th. And if you convert this to precision, this comes out to be 1 over what? Right? So this 0 cancels out this 6 and makes it a 5. So we have 5 zeros. So that's 100,000. And then this 5 divides into the 100,000, and you get 1 in 20,000. So even though the surveyor was able to, with his faulty measurements, calculate that his survey closed to an apparent accuracy of 1 in 50,000, even though he typically calls it precision, it turns out that because he ignored the parts per million correction, that there's no way the survey can be more accurate than 1 in 20,000. And that's not even getting into all the other possible sources of error. We're just talking about the one. What other sources of error are there in this survey? How was this survey actually done? Chances are it wasn't an actual 10,000 foot shot, probably had several shots to get up to 10,000 feet on each side. How many of those did we have? What are the errors in setting up, in sighting, and so on and so forth? So it's very likely that the accuracy may be much less than 1 in 20,000, maybe even as low as 1 in 10,000. And all of a sudden, you start to see the fallacy of some of the thinking that comes up with people who don't have much experience in surveying, which unfortunately includes professional surveyors. So it's very common to have this experience of high precision and low accuracy. And why is this? Because usually surveyors don't calibrate their instrumentation. So if they don't calibrate the instrumentation, they don't know how well it's working. And that's aside from applying all these corrections that I referred to in the previous slide, whether that's a steel tape or GPS or EDM and so forth. Surveyors too often trust the manufacturers to build it right. And as I said, I had a 100-foot steel tape that was not its correct length by a whole foot. So this is blind acceptance of what a manufacturer does just because you pay them a lot of money that is truly misplaced. So what about instrument specs? So instrument specs are usually listed actually as a random error. In fact, you'll often see the term standard deviation or sometimes a certain multiple of standard deviation. So when standard deviation is expressed for instrumentation, it might be something like this. The accuracy of this instrument is plus or minus 1/10 of a foot, or plus or minus 5 seconds for angle measurement, or for GPS, RTK plus or minus 1 centimeter or 2 centimeters plus 2 parts per million. So what do these things actually mean? Well, what they mean is that you can expect, if you have corrected for blunders, if you have corrected for systematic errors, that you can expect 2/3 of your measurement, or about 68% of your measurements, to be inside these ranges. And that's it. That's all you can say. So we'll get into what that implies in the next set of lectures, but I want to talk about what do these specs imply. So I have already said, as I switched from the previous slide to this one, that when you have a plus or minus number, and if it happens to be what we call a standard deviation, that you can only expect to be within that range, that plus or minus range, about 2/3 of the time. That's something that you need to be aware of. There's nothing you can do about it. That's kind of how the mathematics of all of this works. But the other thing is that when the manufacturers test their instrumentation, they do as perfect a job as they can. So let's say they're measuring GPS. They pick a nice wide open area where there's no multipath going on, if you know what that means. If they're using an EDM, they make sure they have highly calibrated prisms, that the plumb bobs, that the optical plummets are perfectly adjusted. They're using a prism pole, that they've carefully checked the level bubble on the prism pole, and so forth. They want every component in the system to be as perfect as possible. Then they will apply all the systematic error compensation from the environment, like temperature, like pressure. And even though it's only half a part per million, they may even calculate the relative humidity and figure out what that correction needs to be. It's only after doing all that that the manufacturer publishes their result. And the thing that surveyors have to ask themselves is, do I actually do all that? Do I always attempt to get as perfect a measurement as I can? And I would say probably not. It's the rare surveyor. Even a responsible surveyor can expect to get less accuracy than the manufacturer tells you you can get. So you have to be very careful about this. This is well beyond the scope of a beginning class in surveying. It's certainly not even within the scope of surveying 2. But I just wanted to point this out because this is one of the things that people think they all of a sudden know everything there is to know about surveying or some other topic from getting a single course. And there are so many layers of understanding and getting into what it is that's really going on, if you will, behind the scenes that you also need to understand. And with that, we will end this lecture.